Yep.
All right, so next thing we'll talk about is called process capability. And so that's on page 53 that is talked about. There's actually just one formula that I would like to have you look at for that. It's typically denoted by C and then a little p. And that is equal to the difference in the specification range divided by 6 times sigma. So what I'd like you to do on your little sheets there is use the first 10 samples to calculate your standard deviation. Does that make sense? So you can use, Brian, the standard deviation calculation formula in Excel or on your calculator. And what I want you to do is you can either make it up or just arbitrarily pick a upper and lower specification of your target. Does that make sense? So typically the way specifications work is you have your normal curve and then your specification lines upper and lower. And so I want you guys to create oh, bless you, your own upper and lower specifications and then calculate this number for CP. Important thing to recognize with process capability is there's also a CPK value, and that is equal to a little bit more complicated formula, but it goes like this. It's the maximum of 2 different numbers. First one is upper specification limit minus x bar divided by 3 times sigma, or x bar minus lower specification times 3 times sigma. All right, so these CP values at times are, as we said earlier in class, used to give an indication of how capable your process is. And the last thing I'm going to show you is how to make a statistical inference based on this. That portion of our work is on we're going to do examples 10.3 and 10.4. So before I do that, is everybody comfortable on how to calculate these 2 equations?
Everyone, what is the difference between CP and CPK?
Yes, thank you for pointing that out, Brian.
What understanding from like what it means.
Right, so CP makes the assumption that if your process were perfectly centered, what would that be? So in other words, if your process is perfectly centered, CP and CPK would be equal to each other.
CP is how repeatable your process is. CPK is how repeatable your process is to its limits that are specified.
That is another factual way to state that. Does that make sense to everybody?
So how do you actually get a CP? Because on these things we just did, we didn't really have an upper spec or a lower spec, right?
Right, and so for the fun exercise in class, I asked you to make up your own.
Oh, okay. And then you divide it by 6 sigma.
6 times the value of sigma, yes.
Okay, what's the value of sigma?
I'm recommending that you do your first 10 to samples, your sample means as your inputs to calculating the signal. So in real life, typically you take, I normally do 25 parts when I do a process capability. Put that into Minitab or Excel. I get my standard deviation calculated. I myself prefer to use Minitab to draw the graphic where it chops the lines off, and it seems more powerful to communicate it that way than the numerical value. I myself do not have all my CP values memorized. Maybe Brian does. Do you have your, what percent fallout do you get if you have a CP of 2?
CP of 2?
Yeah.
That's
Or
not
one.
do anything.
Assuming you have a centered process,
Yes.
CP of 2, you'd have about each 0.3 CP is about 1 standard deviation. So if you have a CP of 2, you're gonna have very little fallout.
Correct.
You're gonna have, that's 6 sigma, so you have like what, 5 in, what's 6 sigma? About 5 in a million?
Right, so the point I was trying to make is it's not, it's kind of an obscure number if you don't have the chart in front of you.
Yes, it's very obscure.
But some companies throw these values around like that you should know them.
The way I try to remember it is 2 is about 6 sigma. So each 0.33 is a standard deviation from the mean. So if you said 0.33, about 66% of your data would fall in. If you said 0.66, about what is it, 95, right? Would fall in. So you can get a general trend that way for ballpark. Chart exactly.
All right, so,
Is tolerance range over 6 sigma?
correct. Yes, that's another way to state it. So you can, as a customer, if you want to change your process capability, you can change your specification limits. Or you can reduce your variation to improve it. Those are the 2 ways to accomplish that. Or, excuse me, there's also the third for the centering of the process.
I think just go backwards sometimes where they're setting up specifications for, you know, what can we do as manufacturing process.
Yep, you could certainly do that.
Sample parts through.
Sure, she could cover.
This is the best that we can achieve, so if we want to do this type of design, this is the variation we can expect through the process.
I think that is a very healthy thing during the design, is to make some type of measurement of your variation that you're capable of doing, and then seeing whether your specification of your design would let that work. So there's that chicken and egg question. Do you make parts, set the specifications off of that? Or do you design and then set your specifications while you're sitting in at your desk? I think both of them are kind of at risk, but it's best to include both of them. Because my frustration is when you get the drawings that show the same tolerance for all dimensions, even though they're made with different processes.
Yes.
I mean, it just, and it's a standard title block, plus or minus 10 thousandths, or whatever the number is. We've all seen them. Yeah, that's never, it's fun when I go talk to engineers that, I'm an engineer too, but you ask them, can we open this up? Oh no, all my tolerances, I've already thought about them, there's gonna be a problem down the road. And, so the last thing I want to get into is being able to make a inference based on this. So we're going to go through example 10.3.
What, how to do the, what? No. You gotta have a separate for that.
Oh, okay.
So in this case, we're asking the
Probably can.
170 pounds. We want to know what's the probability of being greater than that.
0.66.
If we have a process that
Okay.
has a mean of 150 and a standard deviation
6 Sigma.
of 20.
Is there Sigma? Is there Sigma?
Yeah.
So what I like to do is to draw a crude
Yeah.
standard normal. Helps me get a picture of where I'm going at with this.
0.66 times 3.
So I'm interested in everything that is up in this tail, this region here, because I'm at 170. So hopefully you recognize that this is approximately one standard deviation over. All right, so you may remember seeing the equation that looks like this.
Lower, I would say 0. Makes sense. Upper would be.
You guys remember that from 281 stats class? And if the answer is no, do you know how to look up the information for a standard normal table? No? All right, so if you're getting ready for the exam, you need to make sure you find yourself the standard normal table. I don't know if we have that in our book here. If anyone can find that before me and just let me know where that's hidden. Yeah, it's, what page is it? There we are. So it's in the appendix, page 2. And I will come over here to show you. I'll show it up here first. I know you can't see the numbers, but you have a Z table. On the left-hand side, you look first for Z. This is actually equal to Z 1.0. So what we're going to do is we're going to come down this until we find 1.0, come across to 0, 0, and we're going to see the number 0.1587. We're not done that yet,
I said the lower 0.
necessarily, because we need to check to make sure our picture matches the one that's in the book. Because some books will show you the area to the left of the X, some of them will show it to you a number to the right. Yes, so this requires a little bit of patience in that aspect. So, based on that, what can we say about the probability of having someone being greater than 170 pounds? Can anyone tell me what that is in a percentage? It's 15.87%. Does that make sense?
Oh, okay.
Lower than upper.
Correct. Does that kind of make sense? So recall that the whole area under the curve must equal 1. And so we use our Z calculation to look in that table to find this value of 0.1587.
So, can you explain to me how you got the Z calculation?
Certainly, this comes from this equation.
Okay.
X is the question of the point that we're looking at related to the rest of the, it's our question point, if you will. We're wanting to know if we have a population of students with a mean of 150 and a standard deviation of 20 pounds, and we're asking the question, if X equals 170, that's our value here,
Okay.
how many are going to be more than that? So the first thing is to find out what is the z statistic for this point on the standard normal table. So what we're going to do is we're basically going to take our problem written in the language of our interest and convert that to a standard normal table. So that is x, that's the 170. Mu is the average, 20. So that gives us, basically this is a measure of how many standard deviations. That kind of makes sense?
But I'm not sure, you took, I don't understand how you got the 1.
It's the math.
170 minus 20, 150.
Okay, thank you. I told you I'm not good at math.
Well, that's all right. I was kind of cheating because I had the answer in the book, so I jumped to conclusions. But that, yes, good question. All right, so now I'm going to ask another question related to the same information. What is the probability of getting less than 170?
Would it be like 84%?
Less than 170. What did I say?
107.
I'm sorry. Let's make it easier. 170. Thank you. Because we always want to make our problems easy to begin with.
84 point whatever,
And how did you come to that
because
conclusion?
I took the 100% minus 15.8%.
There you go. Does everybody understand that? That if you want to know the area to the opposite side of that x, it's just, because we know the whole area is 1, and it's 1 minus that value. So I guarantee you'll see problems like that on the CQE as well as your final exam. All right, next question is, what is the probability that you would have 150-pound person?
0.
It is not 0. I heard 50. Why did you choose 50?
Because it's halfway.
It's halfway.
That would be below, right?
Yeah.
Not 150 pounds.
Thank you.
The chances
Just
of
'cause it
any
is.
point are 0.
Excellent points to make.
Roll the pen.
I don't have a quick response to the probability of being at a point because there's point estimates, and I don't want to get into that because I'm obviously not prepared to speak about it. With the clarification of less than 150, it is. So the whole point I'm trying to get at is, if you're at the center, it's equally probable to be below that or above it. And it's my suggestion that if you, anytime you set these problems up, draw the picture to make sure you're getting the right tail that you're interested in. Other things you'll frequently run into with problems like this are, let's say that if I ask you to calculate what is the probability of being above your specification limit that you used on your CP values, could you accomplish that? And I would like you to put that on your answer that you turn in for the problem. So we'll put it this way. What is probability over your upper specification limit that you use on your homework assignment for the CP value I asked you to calculate? Does everybody feel comfortable that they could do that?
No.
Nope? All right, so we'll go ahead and do your problem. What is the, let me get some of this. All right. What is your X value, your upper specification limit?
Upper?
Yes.
They calculated it up at 5.39.
Now remember, this is what you set as your specification limit.
What we,
not your average, your upper specification limit.
4.
4?
Yeah. That would, yeah, that sounds right.
One is our lower and 4 is our upper.
Yeah.
So what was the answer still
I would
4?
say 1 would have been our lower specification.
And then what would be your upper?
4.
4?
Is that what
All right.
you're saying?
Or would 0 be the lower specification?
What is your average?
Average X bar?
Yes.
Or the X bar bar?
X bar bar? Be fine.
No, I don't know what that is. I can calculate it up real quick.
And I also want to get your standard deviation.
Standard deviation is 0.66.
I thought you were a number like 3 point something.
That's the positive.
So Keely, do you already have this figured out? You don't? It's your name on the paper. I thought you'd be working furiously.
1.7 is the X bar bar.
1.7, all right. So solve that for me here and tell me what the Z value gets on that.
No changes.
Seems plausible. All right, so we're going to refer to our standard normal out of our appendix.
That's the probability of the international payroll, correct?
So one thing that we should point out is that if you have a Z value of 3, that's typically a really big Z. In fact, it is so big that our book does not even include a number greater than 3. So if that's the case, what do you think the probability is that you would get greater than 4 based on the numbers you gave me here?
Is our Z probably wrong if we got that high in the number?
Nope.
Oh.
That just means you have an excellent process.
Oh, that's the
Any
excellent.
wide specification?
We're a wide specification.
Yep.
So with that, what would be the, to answer this question, what is the probability of getting over the value of 4 based on your example? I think I have this stated correctly, so Brian's not going to challenge me to the number greater than 4.
Probability to get over 4?
Yeah. So our Z value, I'll go ahead and give you a hint. The Z value for 3 is 0.00135. And your Z is greater than 3 even, so it's going to be like, let's say a small number. So cutting to the chase, I would suggest it would be 0. Does that kind of make sense?
Oh, no,
You feel okay with that?
Yeah.
All right, good. How about Keely's? You good with 0? Does everybody else understand why the probability for Joe's group is that it's 0? In other words, our average is 1.7 and 0.66 is our standard deviation. And remember that plus or minus 3 standard deviations is upper 99%. So 3 standard deviations is not going to be anywhere near.
It's what, 50% of what your
suggested your Six Sigma tolerances would be.
So does the rest of the groups know how they would get this answer for your own individual numbers? Ryan's good. Row 3 is all right? Since you're actually gonna turn it in? Yes? All right. How about Shannon's group, you're set? All right, is there any questions over the material we covered today? I did set up a Dropbox for this, Brian, if you wanna submit it that way. And I set it up so that I'm trying something different. You can do a group submission. I've never tried that before, so hopefully that will work for everybody in that back row.
No.
You can either give me your sheet of paper. All right, so there is no gathering next week. Happy Thanksgiving. We'll see you the Wednesday after Thanksgiving. And we're gonna start doing a little bit of design experiments.
Just two of us on that.
That's all right.
Now it's gonna stay in Brookings for about another couple hours.